It's not even recording. Go again.
We're starting.
Okay, so
We're starting the unit on integrals. This is section 4.1, and today we get to learn all of the shortcut rules for antiderivatives.
Oh, cool.
So yes, so we've been doing them the long, difficult way over the last week. Now we get to learn the quick, easy, express way to find all of these answers. You don't even know that we've been doing it, but we have. Yeah, so I'll show you how.
So confused.
Okay. All right. So here we go. Shh. So what we're going to do right now for these first 5 problems is we're going to find a possible function that has this as its derivative. So if f prime is 2x, tell me a possible function f of x that could have 2x as its derivative. X squared. Very good. What about if it wasn't 2x, it's just x?
X squared over 4.
1/2 x squared.
X squared over 2, and I'm going to write it as 1/2 x squared. Treat those numbers that are in the denominator as coefficients if you can. It makes life a little easier. All right. Now we're moving up a degree. So now we have a derivative that's x squared. What function gives you a derivative of x squared?
1/3 x to the third.
1/3 x to the third. Yes, 1/3 x cubed. Because, and you can always check these, right? If you want to check them, just do the derivative. 3 times a third is 1, x squared, right? So, very good. Now this, would this be 1 over 1/3 x cubed? How would I rewrite this function if I wanted to find the derivative?
Square root of x.
No.
Negative 1/3 times
X
x to the negative 3.
Okay, let's just go back to this guy. 1 over x squared is not root x. 1 over x squared is x to the negative second, right? Which is 1 over x squared, has nothing to do with roots. So that would be if the exponent was a fraction, right, rational. So 1 over x squared, this is x to the negative second. Think x to the negative second. So I need a function that gives me a derivative of x to the negative second.
Negative x to the negative first.
Very good. Very good. So we have negative x to the negative first. Because if you do the derivative, you get positive x to the negative second. All right, well done.
Wow.
Last one.
You're a disappointment, Jacob.
This is x to the negative third. I need a function whose derivative is x to the negative third.
Negative 1/2 x to the negative 2.
Let's see. If we multiply this out, we get negative 1/2 times negative 2 is 1x to the negative third. She's right. Okay. All right. Now, how many of you guys got the first one? Yay! What about this one? What about this one? Wow, just about the whole class got the first 3. And then the hands fall down. Some of you, okay, what about this
but I got
one?
that one.
Wow, there were some that got all 5. That's fantastic. Now, those of you that got all 5, did you know the shortcut rule in your head, or did you figure them all out legitimately?
Jacob knew it, but he still got them wrong.
Very good. Very good. All right. So here's my next question. Is x squared is x squared the only function whose derivative is 2x?
No.
Tell me another one.
X squared plus 1.
X squared plus 1. Both of those have a derivative of 2x. Are there any others, or is that it?
X squared
Yeah,
plus 1.
Any
X to the
constant.
3.
X squared
Over-
plus 2, right? Is that it?
X
There's
squared
infinitely
plus
now.
3.
There's infinitely many, right? We could do x squared plus pi, right? Okay.
X
All right.
squared plus
X squared
1.
plus any constant still gives you the same
It'd be like
derivative.
1/3
So do we know what?
times
Is there a
x
way to
to the
figure out what that constant is?
You're going to teach us.
No.
There is no way, not without more information. There's nothing that can divine the constant that went to 0, right? So you have to have more information. So what we do when we write these answers is we have to put a plus c. The plus c represents that unknown constant that was a part of the original function. Now, if we put our plus c for all of these answers are called the antiderivatives of these functions. So if I start with x squared, this would be the derivative of x squared, that would be 2x. If I go backwards and start with 2x, then x squared plus c is the antiderivative of 2x. Alright, so it's the opposite. And the process is also the opposite. So the process of finding a derivative is called differentiation. The process of going backwards is called anti-differentiation. Alright? Okay, and by the way, so now that you've learned it, every time you forget to write the plus c, what's going to happen?
You lose points.
You're going to lose a point, right? Okay, every c, 1 point for every c. Okay, let's do some notation. This hopefully will help some of you who had an issue with trying to figure out those trapezoid rule problems.
Should we write down the integration rules before notation?
Nope, do this first.
Okay. So we can't see it, please? Maybe.
Hey Mustafa, why don't you just stop being so salty?
I'm not so.
Mustafa, how many times have you brought up that you got deferred from tech? Well, now it's gonna be on camera forever.
No.
Mustafa.
Oh.
Man.
But he got accepted to Georgia, so
Like,
that's
who
alright.
else got
He told Obey that he got into tech.
Oh, I did tell my dad I got accepted.
Really?
Yeah.
It's on camera now too.
I'm gonna show Obey the link to
What?
the video.
What if he watches all your
Okay.
videos?
My dad's like, you can have worse problems, still gonna do it.
Okay, quiet
I went
please.
to community college 4 years ago.
This symbol right here
And my mom was
is actually a stretched out letter. Anyone know what letter this is that's stretched out? It's an S. The S stands for sum. Sum. Slytherin, yes. And sum. Alright? This S is an infinite sum. It's actually the sum of infinitely many right-handed rectangles. That S is just a new notation for that infinite sum that we've been doing to find the exact area. And the symbol is called the integral. This is an integral symbol. It's a stretchy S.
Can we call it stretchy ass?
No, call it an integral. Now, the argument of the integral, the stuff in here, is called the integrand. Kind of like the stuff inside of a division symbol is called the dividend, the stuff in a radical is called the radicand, the stuff in an integral symbol is called the integrand.
Those aren't real words.
They are. They are. Some people call the whole thing the integrand, some people just call this function the integrand. I'm not picky, right? So I consider the whole thing part of the argument of the integral, it's the integrand, but you know, it's rarely gonna come up.
Do you actually can you play those words in Scrabble?
I'm sorry?
What if you play those words in Scrabble?
I don't know. Does Scrabble accept mathematical terms?
I don't know.
I don't know.
Can I try?
Which
No,
will
to
make
that.
If he gets buckets, Miss Price.
Can I try?
How about just right
No.
there?
That
You
one's
can try
so
that one.
easy. I make that one all the time.
Goodness.
No.
Alright, now the dx right here, this dx is the exact same dx that you used in derivatives when you had dy dx. So it serves a couple purposes. The first purpose, and I'm just going to keep writing with arrows, it's going to get a little messy, but that's okay. So the dx, it identifies the independent variable. Independent variable.
Should have just pretended like I made it. Nobody else on camera would know.
You just said.
Everyone
Now,
should-
it has a couple other purposes too. dx is actually the limit as delta x approaches 0. Now, in derivatives, your delta x is the difference between the x values of 2 points on a curve, where if you remember that very first day of derivatives, we found slope of the secant, and then we brought the 2 points closer and closer and closer together until it became a tangent. And so what happened was, as we moved the two x values closer together, the delta x, which is the change in x, approaches 0. And that dx actually represents the limit as that delta x goes to 0, because slope is change in y over change in x. Delta y, delta x, right? dy dx is the same thing, it's slope, except that the change in
So
x
that's like the number
goes to
approaches
0.
infinity, it's getting closer to 0.
Yes. So if you guys remember when we did exact area, we did the limit as n approaches infinity, meaning we increase the number of rectangles to infinity. That's the same thing as saying if delta x is the width of each rectangle, take the width and have it approach 0. And that's the same thing as taking the number of rectangles approaching infinity, right? So what we have here is we have, this is your function, so this determines the height of each rectangle. The dx is the width of each rectangle, so we have height times width, there's your area, infinite sum, the sum of the areas of all of those rectangles, right? That's your integral symbol. So the dx is the limit as delta x approaches 0. For you guys right now, all you have to know is that that's why it's there, because it has to be there. It's not going to serve much purpose for you until we get a little bit deeper into integrals. Just like in derivatives, you just wrote dy dx, but you didn't really think about the dx until we got into them a little deeper. It's the same kind of thing. Okay. All right. Now, this answer right here, this is called the antiderivative. Just like with derivatives, there were two types of derivatives. We had general derivatives and specific derivatives. A general derivative is a derivative where the answer is a slope-finding function, right? So the derivative of x squared, the general derivative, is 2x. If I said, hey, f of x is x squared, f prime of x is 2x. If I said, f of x is x squared, what's f prime of 6? And you said, oh, 12, that would be the specific derivative, the derivative at a point, right? Integrals work the same way. We have indefinite integrals and definite integrals. Indefinite integrals give you kind of area-finding functions, and definite integrals give you an area of a specific bounded region. So the answer to an indefinite integral will be a function. The answer to a definite integral will be a number. These, all of what we're doing today are indefinite integrals. Your answer is just going to be a function. An indefinite integral, the answer is an antiderivative. So indefinite integrals and antiderivatives are pretty much synonymous. And you'll hear people say, find the antiderivative of this function and find the integral of this function, and they mean the same thing. When we get into definite integrals, an antiderivative is in no way a definite integral, but it gets used in the process. So the antiderivative is like the indefinite integral of a function. Okay, so there you go. And then of course the C, if you're writing down what all these are, this is called the constant of integration.
Word.
All right, so that's that notation.
So the antiderivative is just the original function, right?
If you consider this the derivative, then the antiderivative would be that original function, yes.
Okay.
Yes. Eventually, you're going to do so many of these, you're not going to think of it anymore as going backwards, you're just going to think of it as its own process. It's kind of like addition and subtraction. You don't really think of subtraction now as the opposite of addition as much as just subtract. It's the same kind of thing. You'll start feeling like finding an antiderivative is just its own thing, like multiplication and division. Okay, but yes, they are inverse operations. Integration rules. All right. There's actually more than just these 5, and we haven't written them down yet, but there we go.
We have for lunch and stuff.
Okay, the first rule is the, oh, I am so sorry, I wrote an X here, this is wrong. It should just be A dx.
Wow.
What if I made a
Say
mistake?
hello to the one on AP exam.
If I made that mistake, -10 on that test.
Yeah, seriously, you should get a -10.
I hadn't turned my paper in yet. See, I still erased it, it's
What
gone.
if a doctor made a mistake like that?
Yeah.
Patient would be dead.
Someone malpractice
This is the
lawsuit.
difference between.
Alright, if I had the antiderivative of the number 5, we need to figure out what function has a derivative of 5. What would that be? 5x, right? The antiderivative of any constant is the constant times x. This is the one that gets, it's the easiest rule, and it's the one that gets missed the most, because you're so used to seeing a constant putting 0, right? So be careful, when you're doing an integral, when you see a constant, it's the constant times x. Excuse me. Now we have the integral of x to the n, this is the Mac Daddy. This is like the integral version of the power rule for derivatives, where you have what's the derivative of x to any power. Here we have the integral of x to any power. Sorry.
Why do you have a leaf in a picture frame?
I have a what?
A leaf in a picture frame?
Oh, a student gave it to me. I thought it was pretty.
If a student gave you a rock, would you keep it?
Maybe.
Really?
I'm gonna get you a rock in the
Yeah, we
picture
get a
frame.
class pet.
Get her a brick. Cut rock.
Okay. This rule, to do this rule, this is a socks, shoes, shoes, socks kind of a rule.
What?
All right? Now,
You should use a
when you
different
get
analogy.
dressed, it's going to be on tape. When you get dressed, if you're wearing shoes and socks, let's say sneakers and socks, we'll go even further. So you put on socks first, then you pull on your shoes, then you tie your shoes. All right? In order to take them off, you have to untie the shoes, then take the shoes off, then take the socks off. Right? So not only are you doing the opposite things, you're doing them in the opposite order to undo them, right? So you don't just do the opposite thing, you do the opposite order. When you take a derivative, just real quick, say I had the derivative of x to the 5th, right? So say real quick I'm doing the derivative of x to the 5th. First thing I do is I multiply out front by the exponent. So first I multiply, take the exponent, put it out front, right? Then I subtract 1 from the exponent. When I'm doing an antiderivative, I got to do opposite thing and opposite order. So the last thing I did was subtracted 1 here. So the first thing I have to do with the antiderivative is add 1 to the exponent, right? Add 1. So if I'm doing the integral of x to the 5th, the first thing I want to do is add 1 to the exponent. Now, when I did the derivative, I multiplied by the exponent. When I do the integral, I have to divide by the exponent. So I don't write it over 6, I put it as like a fraction out front, right? So here's your rule for integrals. First thing you do is raise the exponent by 1, then you divide by the new number, right? Raise the power by 1 first, then divide by the new power. So that's why if you look over what you figured out over here, you had x squared, your new answer is 1/3 x cubed, right? Raise power by 1, then divide by the power. So how do we write that as a rule? Well, x to the n plus 1 over n plus 1. And I'm going to write it as 1 over n plus 1 times x to the n plus 1. And of course we can't forget
Plus C.
plus c.
He's on top of it.
Now there's a little warning with this. This works for every value of n except
0. No, 1. No, negative 1.
negative
There
1.
we go.
Why not negative 1?
Because you can't have 0 in the denominator.
Because that would be dividing by 0. So now we need a rule for x to the negative first. You already know this. No one got it in first period. I'm going to give you a hint. X to the negative first is the same thing as 1 over x. You need to figure out what function has a derivative of 1 over x.
Your head's blocked.
The square root. Something.
There we go.
The square root x.
Right, square root of x.
I don't know.
Negative.
ln. Oh.
X.
Oh, JP.
Hey! You
Smartest
got it!
My boy.
Very good. Okay, the function whose derivative is 1 over x is ln x. Now, there's a little issue with this in that whenever you do the integral, we have to put the x in an absolute value. I will explain why when we get to the natural log unit, which is the next unit. We won't be using this during this unit.
I was so impressive. You're just like
It's really good.
you just
Okay.
casually mentioned it.
The integral of the sum is the sum of the integrals, so you can split it up. Just make sure you put the dx with both integrals. There always has to be a dx or a dy or whatever it is, but there has to be a d something. Oops. So that's that. And then if you have a constant multiplier or a scalar in front of your function, you can take the scalar and put it on the outside and have an equivalent integral.
What if you do composite? Are we not going to learn that?
Oh, like f of g of x?
Yeah.
We will learn that. That actually is the very last lesson of the year.
Boo.
Yes.
Such a tease.
So like.
I also found out they changed something this year.
What?
They changed the day of our AP exam.
When is it?
So our AP exam this is my 13th year doing AP Calculus. Our AP exam has been the first Wednesday in May every year since I've been teaching it. It's now the first Tuesday in May.
Oh, so we have
One
one
day
less
earlier.
day.
Yeah.
What?
One less day to prepare. Okay, there's 2 more quick properties. Okay, these emphasize, quiet down, these emphasize an important concept. Okay, for the 6th rule, this is the antiderivative of the derivative of f.
What?
So you start with f, you take its derivative, and then you take the antiderivative. What do you end up with?
Just x. F of x.
You end up with f. If we start with something, plus c of course, right? If we start with something and we add 5 and then we subtract 5, we're back where we started. Integrals and derivatives are inverse operations. So if you start with something, take its derivative, and then take the antiderivative, you're back where you started. The only difference is that you lost the constant. So,
For
yes.
4 and 5, why don't you add c at the end?
Oh, because we hadn't actually I thought I was wrong, but I'm not. We hadn't actually computed the integrals. Here, we actually wrote answers for these are solutions. These are still we're still in the integral part. So when you write your find your antiderivatives, you would put a plus c.
Yes, ma'am.
All right, number 7, same thing but opposite. Okay,
Throw it in the backpack.
thank you.
Sorry.
That's okay.
That was such a weird.
Now we're starting with f of x, taking the antiderivative, and then taking the derivative.
You still get f of x, right?
You're still at f of x. It's just opposite order. So you still have f of x. One little difference, there's no plus c.
What?
Oh,
I knew that.
what?
Oh, because the c goes away because you're taking the derivative.
Yes, because for this one, we take the derivative last, and so any constants go to 0. All right, any questions on that? All right, good. Let's do some examples.
Yeah, I sat down and it wasn't my class, and I sat there for like 5 minutes thinking it was my class.
What was your real class?
Fifth period.
What was your real class?
Oh no, that was lunch. Yeah. No, so CD is No, CD I have lunch. AD I have if you go.
Nelson, do we have hour lunch?
No, we have to do the post survey. Hey, do you know if do you know if we have like apple lunch like do you know if we have what's it called? A lunch or D lunch or B lunch?
Sack is
Stack. Do we have A
Sack
lunch?
is on top.
We have A stack.
A lunch?
Yeah,
And
on
then B
that
flex?
Hey, guess who else has
Yeah,
A
C
lunch?
Wait.
Guess you have PC
No, we don't
lunch
flex.
today then.
No, but we have to do the survey.
Okay,
Friday.
quiet down
We have to do
please.
the survey.
Now, for these examples, the battery in the camera is about to die.
Just get a long cord.
So I don't have my plug for my camera.
Hand crank?
I know. So I am gonna walk you through these. I wish I could give you a minute to do them on your own, but I don't want to lose this on the tape today. So I'm gonna walk you through them.
We forgive you.
Okay, thank you. So for the first one, we have the integral of 7x dx. Remember, first thing you want to do in your head is raise the power by 1, then divide by that power. So this is 7x to the first, so it's going to be an x squared, and then we got to divide by the 2. So we're instead of 7x to the first, we're now going to have 7 halves x squared.
We
We raise the power by 1, then divide by the power. And then, of course, you always write plus c. All right? Raise the power by 1, divide by the power. Coefficients just come along, just like with derivatives. All right, you guys, tell me the answer to 7x cubed. Beautiful. 7/4 x to the 4th plus c.
Do you
All
want us
right,
to-
I will give you guys 30 seconds right now to do this one. Probably more like 15 seconds.
I'm not even done. I just finished writing it down. Right.
All right, this should look kind of cute when you're done. Did you get something
Is it
kind of cute?
x squared plus x to the 3
X squared
minus x to the 4.
plus x cubed minus x to the 5th
Oh, snap.
plus c.
Because all the
Right?
coefficients.
Because you got
cancel
x
out.
squared over 2 and then those canceled, right? X cubed over 3 and the 3's canceled. And x to the 5th over 5 and the 5's canceled. Y'all good with that?
Yes.
All right. Guys, did I teach you a chain rule for integrals?
No.
No, I didn't. Which means when you hit a problem that requires something that would normally require chain rule for derivatives, you skip it, or you are going to have to get this in a form of x to a power. So you're going to have to multiply this out.
Are you gonna eventually teach us the chain rule?
Yes, but I'm going to call it use substitution.
You couldn't do like.
Okay, so here, here we go. So we have 9x squared minus 6x plus 1 dx. So you just got to FOIL it out. And now take a second, see if you can find the antiderivative.
Is it 1/3 times x cubed?
Close, but there's a 9 there, so
Oh.
3.
you get
Yeah,
3x
my
cubed.
bad.
Okay,
I suck at fractions.
minus 3x squared
Plus x.
plus x plus c. Any questions on that one? One more and we're done. This one's an important one and it's gonna show up over and over and over again.
Don't worry, Miss Price, I got the camera on you.
Do you really? Oh, thank you. Okay, so, I don't have it in front of me, but I'm just gonna
Okay,
see if I can
camera.
remember it. Here we go. Integral of Have I taught you a quotient rule for integrals?
No.
No. So what do you do when you see a quotient?
You gotta
Give it.
You have to split this up.
Kick the dog.
All right, you are going to have to be able to write this as just x to a power. Now, how do you do that? I'm going to show you some intervening steps, but I'm not going to do these every time. Eventually I'm going to get to a point where I'm just going to skip the steps. But I'm just going to, right now, when you have one term in the denominator, a single term, you can split up the fraction where you're dividing each term in the numerator by that denominator.
Could you not break it up? Like,
You could also, and do multiplying, you do the same thing. Yes, whatever you're more comfortable with. Okay, anyone know what x to the first over x to the 1/2 equals?
You lost me. Can you say that again?
This is x to the first over x to the 1/2.
x squared. X to 1/2.
What do you do when you're dividing with exponents? You subtract, so it's 1 minus 1/2. This is x to the 1/2. Which makes sense, right? Anything over its square root would be the other square root. All right, how do I write 1 over the square root of x as x to a power?
X to the negative.
X to the negative 1/2.
Or, yeah, negative half that.
Now, what Rayan said was if we took this root x here and wrote it as x to the negative 1/2 and moved it up here, you could also distribute it in, multiply and add the exponents, right? And that's fine too. You get the same thing either way. Now we do the integral. Be very careful. What is 1/2 plus 1? 3/2. And dividing by 3/2 is the same thing as multiplying by 2/3. What is negative 1/2 plus 1? 1/2. Dividing by 1/2 is the same as multiplying by 2. And then what do we have to write? Plus c. All right, don't forget your plus c's. Every single function has to be written right now as x to a power. If you can't write it as just a x to a power or a sum of x to powers, then yeah, you're probably doing something wrong. No chain rule yet. No product rule, no quotient rule, no chain rule.